For generations, people have described Lake Tahoe as one of the most breathtaking places in North America. The water is so clear that in certain areas you can see more than 70 feet below the surface. The surrounding Sierra Nevada mountains frame the lake like a natural fortress, their snow-covered peaks reflecting in the deep blue water during winter and turning emerald green during summer. To most visitors, Tahoe looks timeless, calm, permanent. But in early 2024, something happened that caught the attention of scientists across the western United States. Lake Tahoe reached its legal maximum water level, 6,229 feet above sea level. That number may not sound dramatic at first, but in the world of hydrology and geology, it carries enormous meaning. Because when Lake Tahoe hits that level, it means the basin is completely full. Every drop of water that the system can legally hold is already there. Any additional inflow must immediately be released downstream through the dam at the Truckee River. And this time, the lake did not slowly creep toward that limit. It surged toward it. After nearly 5 straight years of brutal drought across California and Nevada, the basin experienced one of the fastest hydrological reversals ever recorded. For years, the lake had been shrinking. Boat docks sat above dry sand. Historic shoreline features that had been submerged for decades began reappearing. Marinas watched the water retreat farther away month after month. Local residents worried they were witnessing something permanent. The western United States had entered what scientists called a mega-drought, the most severe dry period in at least 1,200 years, according to tree ring studies. Entire reservoirs across the region were collapsing. Lake Mead and Lake Powell dropped to historic lows. Water restrictions spread across California, and for a while, it looked like Lake Tahoe might follow the same path. Tourism slowed, lakefront businesses struggled, and environmental researchers began warning that climate change could permanently reshape the region's water cycle. But then the atmosphere changed, literally. Beginning in late 2022, a powerful weather pattern began slamming into the west coast of the United States. Meteorologists call them atmospheric rivers. These are enormous corridors of moisture in the sky, sometimes thousands of miles long, that transport tropical water vapor across the Pacific Ocean before dumping it onto the mountains of California. One after another, these atmospheric rivers collided with the Sierra Nevada. Rain fell for days at lower elevations, but higher in the mountains, something even more important was happening. Snow, massive amounts of it. Storm after storm piled snow onto the Sierra Nevada range. Monitoring stations recorded snowpack levels climbing higher and higher until they reached more than double the seasonal average. In some locations, the snowpack measured over 230% of normal. For hydrologists, that number meant something extraordinary. The mountains had effectively turned into a giant frozen reservoir. Billions upon billions of gallons of water were now locked in ice high above the Tahoe Basin. And when spring finally arrived, all of that frozen storage began to melt. The result was explosive. Streams that normally trickled down the mountains turned into roaring torrents. Tributary creeks feeding Lake Tahoe swelled with snowmelt. Water poured into the basin faster than many experts had predicted. Within a single season, the lake rose nearly 4 feet. That kind of increase is extremely rare. Officials managing the water system scrambled to respond. The dam at the lake's outlet along the Truckee River had to be carefully adjusted to release water without flooding downstream communities, while still maintaining the lake's legal limits. Engineers monitored inflows day and night, but the surge kept coming. By early 2024, Lake Tahoe had climbed all the way back to its maximum allowed level. Beaches that had been dry and cracked only 2 years earlier disappeared beneath crystal-clear water. Boat ramps that once ended in dirt were once again submerged. Marinas filled with boats. Tourists returned. Local businesses celebrated. For many people, it felt like a miracle. The lake had survived. The drought had not defeated it. Headlines across California declared that Tahoe had made an incredible comeback. But while vacationers were enjoying the clear water and the renewed shoreline, something else was happening beneath the surface. Something most people never considered. Something hidden deep below the lake floor. Because under Lake Tahoe lies a geological structure that very few tourists, and even many residents, know exists. A massive fault line, one capable of producing a major earthquake. And that fault sits directly beneath billions of tons of water. At first, the changes were subtle. Seismic monitoring stations positioned around the basin began detecting small shifts in the earth. Tiny tremors, so small that nobody standing nearby could feel them. But the instruments recorded everything, each vibration, each microscopic movement in the crust. To the average person, a magnitude 1 or 2 earthquake means nothing. But to seismologists, these tiny events can sometimes reveal deeper stress building underground. Over time, the data started forming a pattern. The tremors were becoming slightly more frequent. Still small, still harmless, but consistent, enough to attract the attention of researchers studying the region. Because Lake Tahoe does not just sit in a scenic mountain valley, it sits inside an active geological basin. The Sierra Nevada mountains themselves were created by powerful tectonic forces stretching the Earth's crust apart. Over millions of years, faults formed along the edges of the basin. Some are small, some are inactive, but one in particular has captured the attention of scientists for decades: the West Tahoe Fault. This fault runs along the western edge of the lake and continues beneath the lake bed itself. Researchers from universities and geological surveys have spent years mapping it using sonar, seismic imaging, and sediment analysis. What they discovered changed how scientists view the Tahoe Basin. The West Tahoe Fault is capable of generating earthquakes far stronger than anything most people associate with the region. Some models suggest it could produce an earthquake reaching magnitude 7 or higher. To understand how powerful that is, consider this. The famous 1989 earthquake that struck the San Francisco Bay Area measured 6.9 on the magnitude scale. That event collapsed highways, destroyed buildings, and caused widespread damage across Northern California. A magnitude 7 earthquake releases significantly more energy. The scale is logarithmic, meaning each increase represents a massive jump in force.
So while a difference of a few decimal points may seem small, the destructive power grows dramatically.
But magnitude alone is not what concerns geologists. The timeline is what makes the West Tahoe Fault so unsettling. By examining sediment layers on the lake floor, scientists have been able to identify evidence of past earthquakes. When large quakes occur beneath lakes, they often trigger underwater landslides that leave distinct deposits in the sediment record. Researchers have extracted core samples from the lake bed and analyzed these layers carefully. The results revealed something surprising. The last major rupture of the West Tahoe Fault appears to have occurred roughly 4,000 years ago. That might sound like ancient history, but in geological terms, it may mean the fault is approaching the end of its normal cycle. Faults accumulate stress slowly as tectonic plates move. Eventually, that stress becomes too great, and the rock fractures suddenly, producing an earthquake. This cycle repeats over thousands of years, and based on the available evidence, the West Tahoe Fault has been quietly building pressure for a very long time, which brings us back to the lake itself. When Lake Tahoe filled rapidly during the atmospheric river storms, something important changed. The total weight pressing down on the lake bed increased dramatically. Water may look light and harmless, but in large quantities it becomes incredibly heavy. 1 cubic foot of water weighs about 62 pounds. Now imagine the volume contained in Lake Tahoe. The lake holds an estimated 39 trillion gallons when full. That is an almost unimaginable amount of mass. When scientists calculate the total weight of that water, the number reaches into billions of tons. And every bit of that weight presses down onto the rocks beneath the lake. Most of the time, that pressure simply becomes part of the natural system. But in certain situations, large bodies of water can actually influence geological activity. There is even a scientific term for it: induced seismicity. This phenomenon occurs when changes in pressure underground alter the stability of existing faults. It has been observed around reservoirs all over the world. In some cases, filling large artificial lakes behind dams has coincided with increased earthquake activity. Water does two important things underground. First, its weight increases vertical stress on the crust. Second, and often more important, water seeps into fractures in the rock. As water fills those tiny cracks, it raises something called pore pressure. This pressure can reduce the friction holding fault surfaces together. In simple terms, water can make it easier for a fault to slip. That does not mean the water alone causes earthquakes, but it can influence when an already stressed fault finally moves. And now consider the situation at Lake Tahoe, a fault that may have been building strain for thousands of years. And above it, a lake that recently filled with billions of tons of additional water. The combination is enough to make scientists watch the instruments very carefully. Because while earthquakes cannot be predicted with certainty, patterns can sometimes reveal when a system is becoming more active. Around the Tahoe Basin, seismographs are quietly recording every vibration in the ground. Day and night, week after week. And the story those instruments are telling is beginning to attract attention. Tiny tremors, small shifts. The Earth adjusting to new pressure. Most of these events are barely noticeable, but they are happening. And they are happening more frequently than before. For now, there is no emergency, no immediate disaster. No sign that a large earthquake is about to strike tomorrow. But what the data suggests is something scientists understand very well. The geological system beneath Lake Tahoe is not silent. It is moving slowly, quietly, responding to forces both ancient and new. Above the surface, tourists continue kayaking across the blue water. Families swim near the shoreline. Boats drift lazily through the mountain reflections. Few people realize that beneath that calm surface lies a fault capable of powerful earthquakes. Even fewer know that the lake now sits at its absolute maximum capacity. Billions of tons of water pressing down on fractured rock that has been storing energy for 4,000 years. For most visitors, Lake Tahoe still feels like paradise. But deep below the lake bed, the Earth is still writing the next chapter of its story. And scientists are watching closely. Because if the West Tahoe Fault ever decides to move again, what happens next may surprise everyone. If you stand on the shores of Lake Tahoe today, nothing feels dangerous. The water is calm, the mountains are silent. Pine forests stretch down the slopes toward the shoreline. Boats glide slowly across the surface while hikers and tourists take photos of what many consider the clearest lake in the United States. Everything about the scene suggests stability, but the truth beneath the lake is very different. Far below the surface, hidden under layers of sediment and fractured rock, lies a massive geological structure known as the West Tahoe Fault. It stretches roughly 25 miles along the western edge of the lake basin, cutting through the earth like a scar that has existed for thousands of years. To the human eye, faults are invisible. You cannot stand on the shoreline and see where they run. There are no cracks on the surface, no warning signs carved into the mountains. But scientists have mapped the fault using underwater sonar, seismic imaging, and sediment analysis taken from deep within the lake bed. The picture they discovered is unsettling. The West Tahoe Fault is not a simple break in the rock. It is a complex network of fractures capable of generating powerful earthquakes. Researchers studying the region estimate that the fault could produce an earthquake measuring over magnitude 7. To understand how destructive that could be, it helps to look at history. In 1989, a powerful earthquake struck Northern California. It became known as the Loma Prieta earthquake. That quake measured 6.9 on the magnitude scale. It collapsed sections of freeway, destroyed buildings, and caused massive damage across the San Francisco Bay Area. Even though it lasted only seconds, the shaking was strong enough to be felt hundreds of miles away. Now imagine something even stronger. A magnitude 7.2 or 7.3 earthquake would release dramatically more energy. The difference may sound small, but the scale is logarithmic. Each step upward represents a huge increase in force. In other words, a magnitude 7 earthquake is not just slightly stronger than a 6.9. It is significantly more powerful. And according to geological studies, the West Tahoe Fault has produced earthquakes of that size in the distant past. How do scientists know this? The answer lies buried in the mud at the bottom of the lake. Over the years, research teams have extracted long cylindrical samples of sediment from the lake floor. These cores act like a timeline of geological history. Layer after layer of material settles at the bottom of the lake over centuries. But when a major earthquake strikes, that calm pattern gets violently disturbed. Underwater landslides sweep across the basin, mixing and displacing the layers in ways that are easy for geologists to recognize. When researchers examined these cores, they found clear evidence of ancient disturbances. Large landslide deposits, massive sediment shifts, signs of powerful shaking that had occurred thousands of years ago. By analyzing these layers and dating the material within them, scientists were able to estimate when the last major rupture occurred. The results surprised many researchers. The last known major earthquake along the West Tahoe Fault happened roughly 4,000 years ago. At first, that may sound reassuring. After all, 4,000 years is an incredibly long time. But in the world of geology, it raises a different concern, because earthquakes on large faults tend to follow long cycles. Over time, tectonic forces slowly push pieces of the Earth's crust against one another. Stress builds gradually along the fault line. For years, decades, centuries, even millennia, the rock remains locked. Then suddenly the pressure becomes too great. The fault slips, and an earthquake is born. Scientists studying the West Tahoe Fault believe that this cycle may take several thousand years, which means something important. The fault may be approaching the end of its natural stress cycle. That does not mean an earthquake is guaranteed tomorrow. In fact, it could still be centuries away. But it does mean the system is already storing enormous amounts of energy beneath the lake, and that energy has been building quietly for thousands of years. Now add something new to the equation: water. When the powerful atmospheric river storms struck the Sierra Nevada, they dumped historic levels of snow across the mountains surrounding Lake Tahoe. The meltwater from that snow eventually flowed into the lake basin, raising the water level dramatically. By the time the lake reached its legal maximum elevation, it contained an almost unimaginable volume of water, around 39 trillion gallons. To visualize that number, imagine billions of Olympic-sized swimming pools stacked together in one place. But water is not weightless. In fact, it is surprisingly heavy. 1 cubic foot of water weighs about 62 pounds. Multiply that by the enormous volume of Lake Tahoe, and the total weight becomes staggering. Billions of tons, all pressing downward on the lake bed, every second, every minute, every day. That weight alone does not automatically trigger earthquakes. But scientists know from decades of research that large reservoirs can sometimes influence fault systems. This process is known as reservoir-induced seismicity. It has been documented in several places around the world. One of the most famous examples occurred in 1967 near the Koyna Dam in India. After the reservoir filled, a magnitude 6.3 earthquake struck the region, killing hundreds of people. Researchers later concluded that the massive body of water may have contributed to the event by altering pressures within the crust. Another example occurred after the creation of Lake Mead, the giant reservoir formed by Hoover Dam. Shortly after the reservoir filled in the 1930s, scientists recorded a noticeable increase in small earthquakes around the area. The explanation lies deep underground. Water does more than add weight. It also seeps into cracks and fractures in the rock below. These tiny pathways allow water to move downward into the crust, where it increases pressure within the rock itself. Geologists call this pore pressure. When pore pressure rises, it can reduce the friction that keeps faults locked together. Imagine two rough surfaces pressed tightly against each other. Without lubrication, they resist movement. But add fluid between them, and suddenly they can slide much more easily. That is essentially what water can do to a fault. It does not create the tectonic forces, those already exist, but it can make it easier for stored energy to release. And that is what makes the situation at Lake Tahoe so interesting to scientists. The West Tahoe Fault may already be carrying thousands of years of accumulated stress. Now billions of tons of water are sitting directly above it, water that is slowly working its way into the fractured rock beneath the lake. And while all of this is happening underground, something else is appearing in the data. Small earthquakes, tiny tremors, events so minor that people standing nearby never notice them, but the instruments notice everything. Around the Tahoe Basin, a network of seismic monitoring stations continuously records vibrations in the ground. These seismographs are extremely sensitive. They can detect movements smaller than the thickness of a human hair. Every tremor appears as a line on a digital screen. Most days the readings are quiet, but lately the pattern has been changing. Small earthquakes measuring around magnitude 1 or 2 have been appearing more frequently along parts of the fault system. Again, these quakes are harmless. A magnitude 1.9 event is far too weak to cause damage. In fact, it is usually too small for humans to feel at all. But to seismologists, these tiny tremors can sometimes act like warning signals. They indicate that the fault is adjusting, releasing tiny pieces of stress, or shifting slightly under new pressure. Scientists refer to this kind of activity as microseismicity. Sometimes it means nothing. Sometimes it is simply the Earth slowly settling into a new balance. But in other cases, an increase in small quakes can occur before larger events. It has happened before in other parts of the world. Prior to the devastating 2011 Tohoku earthquake and tsunami in Japan, researchers later discovered that seismic activity had been gradually increasing in the region. The same pattern has been observed before several other major earthquakes. That does not mean Lake Tahoe is about to experience a disaster. Earthquake prediction remains one of the hardest challenges in science. Even with the most advanced instruments available, researchers cannot determine exactly when a fault will rupture. It could be tomorrow, or it could be centuries from now. But the data tells scientists one important thing. The system beneath Lake Tahoe is not inactive. It is alive, moving slowly, adjusting to new pressures, responding to forces that most people will never see. Above the lake, the surface remains peaceful. The water sparkles in the sunlight. Tourists continue arriving every weekend. Families swim near the beaches. Kayakers drift quietly across the calm blue surface. Few of them realize that beneath their boats lies a fault capable of producing a powerful earthquake. And even fewer understand that the lake sitting above it is now heavier than it has been in years. Billions of tons pressing down on fractured rock. Water slowly seeping into the crust. Tiny tremors quietly appearing in the seismic data. For now, everything remains stable, but deep beneath the basin, the forces shaping the earth are still at work. And the story of Lake Tahoe is far from finished. Because if the West Tahoe Fault ever releases the pressure it has been storing for 4,000 years, the earthquake itself may only be the beginning. Marinas filled with boats, tourists returned, local businesses celebrated. For many people, it felt like a miracle. The lake had survived, the drought had not defeated it. Headlines across California declared that Tahoe had made an incredible comeback. But while vacationers were enjoying the clear water and the renewed shoreline, something else was happening beneath the surface. Something most people never considered, something hidden deep below the lake floor. Because under Lake Tahoe lies a geological structure that very few tourists, and even many residents, know exists. A massive fault line, one capable of producing a major earthquake. And that fault sits directly beneath billions of tons of water. At first, the changes were subtle. Seismic monitoring stations positioned around the basin began detecting small shifts in the earth. Tiny tremors, so small that nobody standing nearby could feel them. But the instruments recorded everything, each vibration, each microscopic movement in the crust. To the average person, a magnitude 1 or 2 earthquake means nothing. But to seismologists, these tiny events can sometimes reveal deeper stress building underground. Over time, the data started forming a pattern. The tremors were becoming slightly more frequent. Still small, still harmless, but consistent, enough to attract the attention of researchers studying the region. Because Lake Tahoe does not just sit in a scenic mountain valley, it sits inside an active geological basin. The Sierra Nevada mountains themselves were created by powerful tectonic forces stretching the Earth's crust apart. Over millions of years, faults formed along the edges of the basin. Some are small, some are inactive. But one in particular has captured the attention of scientists for decades: the West Tahoe Fault. This fault runs along the western edge of the lake and continues beneath the lake bed itself. Researchers from universities and geological surveys have spent years mapping it using sonar, seismic imaging, and sediment analysis. What they discovered changed how scientists view the Tahoe Basin. The West Tahoe Fault is capable of generating earthquakes far stronger than anything most people associate with the region. Some models suggest it could produce an earthquake reaching magnitude 7 or higher. To understand how powerful that is, consider this. The famous 1989 earthquake that struck the San Francisco Bay Area measured 6.9 on the magnitude scale. That event collapsed highways, destroyed buildings, and caused widespread damage across Northern California. A magnitude 7 earthquake releases significantly more energy. The scale is logarithmic, meaning each increase represents a massive jump in force.
So while a difference of a few decimal points may seem small, the destructive power grows dramatically.
But magnitude alone is not what concerns geologists. The timeline is what makes the West Tahoe Fault so unsettling. By examining sediment layers on the lake floor, scientists have been able to identify evidence of past earthquakes. When large quakes occur beneath lakes, they often trigger underwater landslides that leave distinct deposits in the sediment record. Researchers have extracted core samples from the lakebed and analyzed these layers carefully. The results revealed something surprising. The last major rupture of the West Tahoe Fault appears to have occurred roughly 4,000 years ago. That might sound like ancient history, but in geological terms, it may mean the fault is approaching the end of its normal cycle. Faults accumulate stress slowly as tectonic plates move. Eventually, that stress becomes too great, and the rock fractures suddenly, producing an earthquake. This cycle repeats over thousands of years, and based on the available evidence, the West Tahoe Fault has been quietly building pressure for a very long time. If the West Tahoe Fault were to rupture tomorrow, the earthquake itself would be terrifying. But for the communities surrounding Lake Tahoe, the shaking might only be the first phase of the disaster. Because beneath the lake's calm blue surface lies a landscape that most people have never seen. The bottom of Lake Tahoe is not flat. It is not a gentle bowl filled with water. Instead, the basin drops away sharply in many places. Massive underwater cliffs descend into darkness, some plunging thousands of feet below the surface. The lake is astonishingly deep. In fact, with a maximum depth of more than 1,600 feet, it is the second deepest lake in the United States. Those depths create steep underwater slopes surrounding much of the basin, and along those slopes lies something potentially dangerous: loose sediment. Over thousands of years, layers of sand, mud, and organic material have slowly settled on the lake floor. These layers form thick deposits that cling to the steep underwater terrain. Most of the time, they remain stable. Gravity holds them in place. But strong earthquakes can change everything in seconds. When the ground shakes violently, those underwater slopes can collapse. Millions of tons of sediment can suddenly break free and rush downhill into the deepest parts of the basin. Scientists call these events submarine landslides. And when they happen inside a confined body of water like Lake Tahoe, they can produce something most people never associate with mountain lakes: a tsunami. The idea may sound strange at first. Most people think of tsunamis as ocean disasters triggered by massive earthquakes along distant coastlines. But the physics of tsunamis is actually very simple. Whenever a huge amount of water is displaced very quickly, waves form. If enough water moves at once, those waves can become extremely powerful. In the ocean, tsunamis are usually caused by earthquakes that lift or drop the seafloor. But inside lakes, the most common trigger is different: landslides. When a giant mass of rock or sediment crashes into the water, it pushes enormous volumes of water outward in every direction. The larger the landslide, the larger the wave. Lake Tahoe has experienced this before. Deep beneath the lake floor, researchers have discovered evidence of ancient underwater landslides preserved in the sediment record. One of the most dramatic examples lies near an area known as McKinney Bay Landslide Complex. At some point thousands of years ago, an enormous section of the lake bed collapsed there. The landslide moved an estimated 12 cubic miles of material. To put that into perspective, that is enough earth and sediment to fill millions of dump trucks. When that mass plunged into the deeper basin, it would have displaced an enormous amount of water. Scientists studying the deposit believe it likely generated a massive wave across the lake. At the time, there were no cities around Tahoe. No marinas, no lakeside homes. The shoreline was mostly wilderness. But if something similar happened today, the consequences could be very different. Modern computer models have attempted to simulate what might happen if a major earthquake triggered a large underwater landslide in Lake Tahoe. The results are sobering. Some scenarios suggest waves 30 feet high or more could form along certain shorelines. Those waves would not move slowly. In a lake as deep as Tahoe, tsunami waves could travel at speeds approaching 100 miles per hour. And because the lake is relatively narrow compared to the ocean, the wave would cross the entire basin extremely quickly. At its widest point, Lake Tahoe is only about 12 miles across. A wave generated on one side could slam into the opposite shoreline in just a few minutes. That leaves very little time for warning. Along ocean coastlines, tsunami monitoring systems can detect earthquakes thousands of miles away. Alerts are sent out hours before waves arrive. Evacuation sirens give communities time to reach higher ground. But Lake Tahoe is different. Here, the earthquake and the wave would likely arrive almost at the same time. Residents would feel the ground shaking, and within minutes the water itself could begin rising. There is another complication as well. Lake Tahoe is a closed basin surrounded by mountains. When waves strike the shoreline, they do not simply disappear, they bounce. Reflections from the shoreline can send waves back across the lake, where they collide with incoming waves and create complex patterns of motion. That means the first wave may not be the last. Multiple waves could strike different communities as water surges back and forth across the basin. For towns built directly along the shoreline, the timing could be devastating. Communities like South Lake Tahoe, Tahoe City, Incline Village, and Kings Beach all sit only a short distance from the water. Many homes, restaurants, and hotels are built just feet above the lake level. During a busy summer weekend, the population around the lake can explode. Although only about 55,000 people live in the basin year-round, tourism brings in huge crowds. On holidays and peak summer weekends, more than 100,000 visitors can surround the lake. Beaches fill with swimmers, marinas fill with boats. Roads fill with traffic. The region was never designed for rapid evacuation. Most of the highways entering and leaving the basin are narrow mountain roads. During normal vacation traffic, they can already become congested. If thousands of people tried to leave at once, gridlock would form quickly. And in the scenario scientists worry about most, there may not be time for evacuation at all. The earthquake would strike first. Buildings would shake, power lines could fall, roads might crack or collapse in places. And before emergency systems could even assess the damage, the water itself could begin moving. The shoreline would experience a sudden and powerful surge. Boats could be lifted and tossed inland. Docks and piers could snap under the force. Low-lying structures along the waterfront would be directly in the path of the wave. The geography that makes Lake Tahoe so beautiful also creates this vulnerability. Steep mountains surround the basin. Communities naturally developed along the narrow band of flat land near the water's edge. It is the most scenic part of the lake. But in a tsunami scenario, it is also the most exposed. Yet despite the possibility, very few people around Tahoe are aware of the risk. Unlike coastal regions threatened by ocean tsunamis, the lake does not have widespread warning systems. There are no shoreline sirens specifically designed for tsunami evacuation. Few public signs describe evacuation routes, and most visitors who come for skiing, hiking, or boating never imagine that a mountain lake could produce waves of that size. Part of the reason is simple. The event scientists are describing is extremely rare. It requires a specific chain of circumstances, a powerful earthquake, an underwater landslide large enough to displace enormous volumes of water, and communities positioned directly in the path of the waves. But rare does not mean impossible. Geological evidence shows it has happened before. The landslide deposits beneath the lake are proof of that. And while researchers cannot predict when another event might occur, they do know one thing with certainty. The fault beneath Lake Tahoe is still active. The basin continues to experience small earthquakes, and the lake above it is currently filled to its maximum capacity. For now, the water remains calm. Sunsets still paint the sky orange and purple over the mountains. Kayaks glide across the surface. Visitors continue to photograph what they believe is one of the most peaceful landscapes in America. But beneath that surface lies a dynamic geological system that has been shaping the region for millions of years. A system that moves slowly, quietly, and unpredictably. And somewhere deep beneath the water, the pressure continues to build. The earthquake may not come tomorrow. It may not come this decade. But the forces beneath Lake Tahoe have never stopped working. And if they ever release that energy all at once, the lake itself could become the source of a wave no one along its shores would expect.